So today I will be sharing how we can effectively facilitate mathematical discourse in an algebra classroom. So in this presentation, I will focus on how we as teachers can create classroom environments where students can actively engage in mathematical discourse. I will share some strategies, examples, and some routines that might help promote rich conversations in algebra. We'll start by defining what mathematical discourse is and its role in effective teaching. And then we'll look at some research foundations, classroom strategies, and two tasks that I created that'll model these ideas. So mathematical discourse refers to the purposeful exchange of mathematical ideas through spoken discussion, written explanations, or visual representations. Now, in the classroom, discourse is more than just talking. It's getting the students to explain and justify and build the connections between these multiple representations to help deepen their understanding. So mathematical discourse supports students in developing a much stronger conceptual understanding because it pushes them to make connections. It also promotes the use of precise mathematical language, which strengthens communication skills and supports students in justifying their thinking. And overall, these experiences build confidence and help position students as capable mathematical thinkers. So for teachers, mathematical discourse gives us valuable real-time insight into how students are thinking and making sense of ideas. It helps us to identify these misconceptions or gaps in understanding much more quickly than just a written work. These conversations also support us in refining our instruction and also allows us to determine whether students are developing a conceptual understanding or just relying on procedures. So to support meaningful mathematical discourse, we have to establish norms that encourage open, respectful, and mathematically focused communication. We also have to model these practices in front of our students so that they can get a better sense of what it means and what it means to be productive. It's also important to emphasize that mistakes and questions and differing perspectives within the classroom are welcome and essential for learning so that we can create a classroom culture where all students feel comfortable in contributing their thinking. Now, to foster meaningful discourse, the tasks that we choose are really important. We want high quality tasks that promote a high level of cognitive demand. We also want them to encourage collaboration across multiple representations. And when these tasks incorporate multiple representations, students just naturally have opportunities to discuss things. The other important thing is that we want to establish clear mathematical goals that guide discussion and reasoning. Now, before teaching, it's important to anticipate different student responses to the task. Um, Thinking through these possibilities ahead of time allows us to prepare for questions that'll help with deepening understanding. It'll also allow us to anticipate any misconceptions that might show up during the lesson and allow us to plan for how we will address those during instruction. Now, while students are working, we are now facilitators of guiding these conversations. There's talk moves that we can use. There's assessing and advancing questions that we can use. We can also use this time to select and sequence students' responses so that they can present that during a whole class discussion. So here's an example of some talk moves that help us press for reasoning, clarify ideas, deepen the student's mathematical understanding. And so this has a describes what each of the different moves are, and some direct examples of those moves. So assessing questions, these are the questions that help us understand where students are in their thinking, and allow us to like push them to clarify what they've already know. And then advancing questions is kind of pushing students towards reasoning and encouraging that deeper mathematical understanding. So the examples shown here illustrate how these two types of questions look in practice, using both intentionally, you have to use them intentionally, allows us to support students' understanding. So after students work in their groups and we bring them all back for a whole class discussion, they can present their their work. And as they share, we want to again encourage them to explain how they arrived at their answer, use precise mathematical vocabulary, can work with them to compare strategies, discuss similarities, connect all of the different methods. And this dialogue here is just an example of a sample dialogue and some moves that you could use in certain instances to get that across. And then, as always, we can address any misconceptions in real time as they come up. Now, this example, it's just another example of what mathematical discourse and like a whole classroom discussion could look like. So this one, specifically highlights student-to-student discourse using mathematical vocabulary, demonstrates how the teacher can press for reasoning and help clarify concepts. Now we come up with reflection. It's an essential part of meaningful mathematical discourse. We want to give students the time to summarize their ideas and the connections that they've made. Now, us as teachers, we need to gauge the individual understanding, and we can do that by giving a formative assessment like an exit ticket or a written reflection, things like that. And then as teachers, we can review our observation notes from the lesson to help us plan for next steps, refine our future instruction, and so forth. So the following tasks I've designed are just here to illustrate how these discourse practices look in a real lesson. So task 1 is a shopping translations task. The students are given a list of some real-world college-related purchases that are written out, and the goal is to write them into an algebraic expression, substitute a given value into their expression, determine if they can afford all the items that are wanted or needed, and then justify the reasoning and the decisions that they've made. This is just kind of a slide for the mathematical goals of this task. So we want them to be able to translate verbal descriptions into algebraic expressions. We want them to be able to evaluate these expressions for given values and then explain the reasoning. I also included kind of a part of like when students will be successful. So in this case, they'll be successful when they can correctly represent each situation, when they can calculate the cost accurately and correctly, and they can justify their decisions. And all of these goals, again, just help ensure that the discourse that students are engaged in is grounded in these mathematical ideas that we want them to develop. So these tables here illustrate some examples of common um, algebraic expressions or correct algebraic expressions, and then some common student variations that might happen. Um, this also includes some misconceptions or errors that they might make while writing their expression or evaluating their expression. And this helps guide the development of some, questions that happen later. So this is a graph and a table that I wanted to include, that I thought that students might use during this task, to visually compare their income to total expenses, and to help them decide whether they have enough money and which items they might want to remove. Because approaches like this, seem to kind of spark those discussions as students talk about the items that they want versus what they don't want and justifying those choices. So here I have, some assessing and advancing questions that I might use, as I would be walking around the classroom and listening to the conversations that are taking place. Some of these might be more to, get them to clarify understanding, push reasoning a little further. And using these questions intentionally helps guide groups towards the mathematical goals of the lesson, but it also kind of keeps them engaged in the discourse itself. So you don't end up with one person in a group that's just not participating or not talking. And then as I'm walking around and I'm listening, I'm also going to make notes of, um, some sequencing of, if I'm going to have them present, what order do I want them to present in? Um, and write that down. What order makes more sense to support mathematical connections? Or what connections do I want them to make first versus last? Um, and so here I just kind of made a list of the order that I would have them presented in, um, and some questions that I could ask during a whole class discussion for each of the groups, and then just some general questions that I could ask as all students as a whole. And then to wrap up the task, in the last 5 to 10 minutes, I try to give the students some time to summarize the key ideas, clarify, or reinforce any important information that I needed to. And in order to check for individual understanding, I would probably give an exit ticket similar to this one, um, just to check the individual understanding of the material that we had covered for the day. Now on to task 2, the parking lot task. So in this task, they are given a real world scenario involving a full parking lot and two types of vehicles. They're given the total number of occupied parking spaces, they're given a total wheel count, um, and then the two categories of vehicles. And then on to the mathematical goals of this task. They will learn how to model this scenario using a system of equations. Um, they'll learn how to solve the system using an appropriate method and then explain that solution, um, that makes sense in the context of this problem. Students will be successful when they can define the variables, write the equations, represent the vehicles and the wheels, solve it accurately, and clearly justify why it's correct. And then here we have some common responses and misconceptions. So like here we have at the top, solving using substitution, solving one equation using substitution, but students could distribute incorrectly, right? Or table and guess and checking, and some of the things that might, um, be a misconception with working the problem in that particular method. And these are, this is just a continuation of like, this is solving a system with substitution and the various ways to solve it and some of the possible errors that could happen um, as students work through that particular solution path. And the same here, but this one's with solving it by elimination instead. And then this is a graphing because they could also graph this. So this was like an example of like the table and the equations that they'd come up with and the graph that they could make in Desmos or the graph that they could make in their calculator and some possible errors that could happen along the way. And this is like a drawing. Some students may try to model the problem by drawing the parking lot. While this isn't the most efficient or preferred method of solving this task, it is a starting point and it does kind of help create some questions to redirect them towards a more algebraic reasoning. And then here are the assessing and advancing questions that I would ask for this task. What assumptions did you make? Push their thinking a little bit further, encouraging them to analyze patterns, make connections between the total number of parking spots, finding alternative ways to solve the system, things like that. And then again, this is like my sequencing. So this is how I would want to sequence the group's presentations to the class and some questions that I could ask them during a whole class discussion to further connect all of these representations. And then again, to close the lesson, I would have an exit ticket to monitor the individual understandings per student. And then also I have like a list of like reflection questions for myself for after the lesson. So I can go back and kind of reflect and review on the lesson to make changes as needed. So overall, both of these tasks support meaningful mathematical discourse by giving students multiple entry points, multiple solution paths, authentic opportunities to explain and justify their thinking. So task one lays the foundation by helping students translate between verbal and algebraic. Task two builds on that by asking students to model a real-world scenario. And then by anticipating these student responses and misconceptions allows us to plan those purposeful questions, guide their thinking, support their struggle throughout the lesson. And by monitoring and all of these practices that we can incorporate, we can orchestrate a whole class discussion that connects all of these strategies and highlights all these important ideas and moves students towards this mathematical goal at the end of the day. And these are some of the key sources that I used to design the task and the emphasis of on discourse throughout this presentation. They include foundational work from Smith and Stein on the 5 practices and CTM's principles to actions and several other articles that are focused on facilitating meaningful mathematical conversations. So together, these references ground the lesson design and research-based practices that support student reasoning, collaboration, and conceptual understanding. Thank you for listening.